Hello, hello. Is this working? It's going to be slightly complicated holding both this and this, so if I start holding this up to my mouth, just someone wave at me. So as developers, our bounds and our responsibilities in the industry have changed all the time. If you think back to the start of the web, it was just text on a screen, and our goal was to have that text be read by someone else. And that was actually quite difficult because there wasn't really anyone else on the internet. But then we got more and more developers working on the internet, and we had to compete. We wanted to compete with other developers to show that we were better than they were. And we did this by putting our pages in outer space and centering things and moving things from side to side. We really liked the moving bits on the web, so we added a whole bunch of them, you know? Make it look like there's loads of complicated stuff going on, because the more complicated it looks, the more complicated it must have been, and that makes us better developers. We discovered JavaScript at this point, and we used JavaScript to create grey dialogues on the screen. But then we looked around, and we realized that the internet had been infiltrated. It had been infiltrated by normal people. And it was like our parents had been away for 10 years, and we've been all having this great party, and all of a sudden they phoned and said, "We're coming home." And we're like, "Oh my God, look at the mess we've made. We need to clean this up." And we did. Usability became a big deal. The GIFs, the marquees, no longer cool. We started thinking about readability, semantics, accessibility. It was a real back to basics move for the web. We got a new browser war at this point with more budget and bigger explosions than the last browser war. And Netscape was killed off in the first scene, but some of the new characters were pretty good. We had the Chromes, the Firefoxes, the Safaris. A new generation of developers had to care about this platform and browser compatibility. We started using JavaScript properly. CSS became more powerful. And then our testing surface area exploded. This happened. Now we had to care about the different interactions and user experience of all these different devices. And this is pretty much where we are now, except GIFs are cool again, as long as they're like 3 megabytes in size and they're of a cat doing a thing. But until fairly recently, we'd taken an odd stance when it comes to graphical performance. Our goal was usable. Not good, usable. On machines that could draw 3D worlds fast enough to respond to gaming controls in real time, we were happy for our 2D, fairly static pages to perform just a little bit better than unusable. Well, that's not good enough anymore. Facebook did an experiment where they artificially decreased the performance of their mobile app. They kind of decreased the frame rate. It was still usable, just not as smooth. And when they did this, they saw a significant drop in engagement. If you're not caring about graphics performance, then your users are going to go to someone who does. And this wasn't possible until recently because the browsers didn't really let us deliver fluid user experiences, but they've all made a leap forward, all of the browsers, IE, Chrome, Firefox, Safari. But as developers, we still have to meet them halfway. There's a few things we have to do in order to deliver this fluid user experience. And DevTools are here to help. We saw Paul Irish talking about this earlier. The timeline shows you all of the stuff that's going on in the background as Chrome builds up a page. But what are all these steps? What do they mean? And what causes them to happen? How does the browser get from data to pixels? Well, in the beginning, there is nothing. And then, like a burst tap, the browser is sprayed with HTML text from the internet. And it will convert that text into a tree of elements that we know as the document object model, the DOM. This step in the process is, I'm sure you know already, called parsing. And this will show up in the timeline there, parse HTML. You'll see this as the page initially loads, but you'll also see it if you pass an HTML string to particular JavaScript interfaces like inner HTML. You'll see parsing happening there. We haven't drawn anything at this point. The screen is still blank. At this point, the browser needs to know what these elements look like and where they appear on the page. And this starts with a style calculation. This looks at the CSS cascade, the style attributes, your font tags if you're from the 90s, and it works out which styles apply to each element. And this event shows up on the timeline. We saw Paul talking about this earlier, recalculate style. You'll see this whenever you load a CSS file, when you change the style object on an element, when you change a class name, or when you move the DOM tree around. Some of these elements didn't get their style calculated. This paragraph here and this div, they didn't get their style calculated. And this is because when we looked at this div, it turned out to be display none. And this is where the browser will make a shortcut, because there's no point thinking about the styles of these elements because they have no impact on the visual output of the page. So it will shortcut at that point. We haven't drawn anything at this point, of course, because although we know which styles apply to each element, we don't know how those styles interact with each other. We don't know the size and position of each element. To do this, we create another tree internally in the browser, a render tree. And this knows where everything sits on the page and how big it is. This process is called layout, and that appears in the timeline as well. Changing the DOM causes a layout. Style changes may cause a layout. Like if you change the border size of something, you'll get a layout. But if you change the background color, that doesn't impact where things appear on the page, so you don't get a layout there. But even things like resizing the browser, that's going to cause a layout to happen. You'll notice that these trees are similar, but they're not exactly the same. For instance, this heading here has a render object, but there's also a child render object that doesn't appear in the DOM. And in this case, this is a CSS pseudo element, like before or after, that will create itself a render object. We see this video element here. This video element has an element in the render tree, but in the render tree there's always this series of render objects that aren't in the DOM. I feel like a weatherman doing this. It's great. So this is the video element shadow DOM. These are the elements that make up the slider, the volume control, etc., etc. Also, we have this div here, which doesn't appear in the render tree at all. And that's, as I said before, it's display none. It has no visual impact on the page, so it doesn't go into the render tree. We still haven't actually drawn anything yet, of course. At some point, the browser will decide that an area of the screen is showing the wrong thing, which could mean because it's blank, or you've updated part of it. And what the browser will do then is it will identify the render objects that form part of that page, and it will create drawing instructions, create pixels for that data, and send them off to the GPU, and they appear on the screen. And that process is paint, and it will show you how much was painted and when it happened. Paints are caused by visual changes. That can be triggered by DOM changes, style changes, layout changes, but even just highlighting text on the page, that's going to cause, or like hover effects, they're going to cause paints to happen. And that's a lot of stuff for the browser to do, and we know how to measure it. But how fast should it be? We want it to be instant, but how fast is instant? The consensus is you want to update the screen within 100 milliseconds of interaction. This is an article I see cited. This is the United States Department of Defense Design Criteria Standard, which I hope is easier to say in Korean than it is in English. These figures are from 1999, so maybe expectations are a bit higher now, but 100 milliseconds still feels right to respond to a user interaction. Let's have a look at an example. So here I've got these rainbow colors here, and if I click on them, they change to a different color, the opposite color in the hue. And the code for that's really, really simple. All I'm doing is I'm looping through all the elements that are here, assigning them a color, and then on click, it's going to swap the color to the opposite hue. It's pretty quick. But if we look at it on mobile, it's really, really sluggish. Feels really, really slow. Mobile phones are slower than desktop, but they're not that slow. This isn't caused by poor hardware performance. This is an event issue. You see, with mobile phones, you can pinch zoom, but you can also double tap to zoom into some text. And this is a problem, because it means on every tap, we have to wait. We have to wait to see if you're going to double tap. And that wait is 300 milliseconds, and that's there. So if we're saying 100 milliseconds feels instant, you are already 3 times over that before you even get a chance to run any code, which is a big problem. We could fix this by, instead of using click, or as well as using click, we could use touch end. And that's great. Oh, loads faster. Excellent. But at the end of scroll, we wouldn't expect that, because that's still a touch end. Or this is how it works in most browsers. This is how it works on iOS, the old Android browser, and Firefox. Chrome won't fire a touch end if scrolling happens, but it's kind of, I think we're going to switch to doing the same thing as everyone else, just to be consistent. Everyone's doing it right according to the specification. The specification is really, really vague. Microsoft's pointer event spec does the right thing. It specifies what should happen, and it says if scrolling takes place, you don't fire a pointer up because the events have been taken over by the hardware. Unfortunately, there's not a lot of support for this. And even then, we'd only be able to use this when we're dealing with events in JavaScript. What if the user's just clicking on a checkbox or an input or a link? We want that to be faster as well. This library is really great. It's by the Financial Times, called FastClick. And what that does is it uses a series of touch listeners, but it also analyzes how far the page is scrolled in between or how far the user's finger has moved in between. And it will try and fire click events as soon as it can at the expense of double tap. You lose the double tap gesture, but your clicks become a whole lot faster. Alternatively, if you have a viewport on your page and it's fixed, double tap doesn't mean anything because you can't zoom. So we get rid of the 300 millisecond delay, which is great. This only works in Chrome on Android and Firefox on Android. But even then, pinch zooming feels like a really nice accessibility feature, and it's something people expect of the web. We're at the moment in Chrome, we're looking at ways that we can get rid of that 300 millisecond delay, even on pages with some degree of zooming. We're hoping to land that later this year. But in the meantime, the Financial Times FastClick script is absolutely brilliant. So 100 milliseconds feels instant, and anything over that, not so much. What about this? This is some snow, where it animates 1 frame every 100 milliseconds. Here's a touch action, where this square updates every 100 milliseconds. 100 milliseconds is not good enough for animation, and it's not good enough for continual touch feedback. If we see our apps performing like this, we must ask what the frames per second is going on here. And in that case, it was 10. 10 frames per second was going on. And if that's not good enough, what is? You have to excuse me because I get to nerd out about frame rates a bit. When cinema with audio was introduced, a standard emerged that frames should be 42 milliseconds apart, which makes it 24 frames per second. Film, a series of stills where the light is shone through the film. 24 was picked because film was quite expensive and they wanted to go as low as possible. So 24 isn't good. It was just decided that that's one better than unwatchable. And things stayed like that for 90 years. The Hobbit being the first film to really, mainstream film to change that. That went up to 48 frames per second. Meanwhile, this was happening. People were getting color TVs in their homes. And in CRT screens, it's created by an electron gun, which sounds really sci-fi, and it looks really sci-fi as well. That's a TV electron gun. It beams the picture starting from the top, scans to the bottom, and then restarts. And it did that 60 times a second here and the US. In a lot of the rest of the world, it was 50 times a second. That's the refresh rate of the screen, and it's also the maximum frame rate. 50 and 60 were chosen because it depended on the power supply frequency of the country. And back when the first TVs were out, it was much cheaper to make them if you could rely on the power supply as the timer, rather than sort of building that into the TV. So that's where the difference comes from. So some TV shows would go up to 50 or 60 frames per second. Some TV shows would choose to miss out every other frame, and it would make them look more like film, because they'd be at 30 or 25 frames per second. And this is why The Hobbit, at 48 frames per second, kind of felt like a cheap soap opera or a computer game to people, because it's what they associate that frame rate with. Computer monitors could be driven at different refresh rates. 50, 60, quite painful on the eyes. We tended to drive them at 75, 100, even 120. We don't use CRTs anymore. We use flat screens. Not as good for cats to sit on top of, but better for our eyes. These screens don't scan in the same way as CRT screens. A higher refresh rate isn't really beneficial. 60 is the most common one we see now. You'll encounter the odd projector or screen that wants to be at 75, and some laptops will go down to 50 when they're running on battery power. So when we want smooth motion, that's our goal. We want to deliver a new frame for every refresh of the screen. And at 60 Hertz, that's 16.67 milliseconds. That's our deadline. And that's not long to edit the DOM, calculate style, layout, paint. And on a mobile, you've got less processing power, so that feels like less time. However, most instances of animation on the web are shooting themselves in the foot. They're not starting their work early enough, or they're overworking the browser. If your frame, let's see, here's our refreshers, each one of them 16.67 milliseconds long. Say our frame takes 10 milliseconds to construct. That's great. That will appear in the next refresh. That's when the user will see it. But when do we start building the next frame? We could go as soon as possible. This is the code for that. Set timeout, 0. And that looks like this. And that work goes into the refreshes. However, some of the frames we created never actually ended up on the screen. We're making too many of them. And this is going to be using too much of the CPU, which means too much of the battery on devices with battery. And at some point, another application is going to come along and go, do you mind? I would quite like a go on the CPU now. And the scheduler will block what you're doing and let this other app have a go, and you will drop frames. So this is wrong. What could we do? We could do set timeout 16.667. This is pretty much what jQuery does. Set timeout and set interval only promise that your function is going to be called after the number of milliseconds you give it, and it's rounded to an internal timer that isn't very accurate. So the first 4 frames turn out fine, but we're out of sync. The work is starting later and later into the refresh until here, when we miss our deadline. That is going to go into the refresh after we have skipped a frame. But this is still 58 frames per second, roughly, and that's pretty good. When it comes to orange juice, who prefers orange juice with bits of orange in it, like little bits of orange? One guy, Alex, okay. Who prefers their orange juice smooth? We've got lots of people with no opinion on orange juice at all. That's fine. I prefer it smooth. I had this debate with someone at work, and they said, no, I like to have an orange juice that I can chew. They're going to be over the moon when they discover oranges. It's everything they want. But imagine you're drinking a glass of milk. And when you're drinking the glass of milk, a lumpy bit goes into your mouth. It's not expected. It's not nice. Well, that's like animation. Animation is like smooth orange juice, milk, and farts. Lumps are unexpected and unpleasant. We don't want them. Have a look at this. This snow is animating at half the refresh rate of the screen, which is 30 frames per second. And you study the motion of some of the bigger bits of snow as they come down the screen. It's pretty consistent. If we go to use set interval, this is how jQuery does it. If you follow the bits of snow down, it's kind of juddery and jerky as we're getting out of sync with the refresh rate. This is a higher frame rate than we saw before, but it looks worse because it's uneven. It's uneven because 58 frames per second does not divide into 60 Hertz. It doesn't divide into the refresh rate of the screen. The highest possible frame rate is less important than staying divisible by the screen's refresh rate. So how do we solve this? Well, it was mentioned earlier. We want to use request animation frame, but this is how it works. It will make sure your JavaScript is called right at the start of the refresh of the screen. And this gives you the full 16.67 milliseconds to get your frame ready. It gives you the best possible chance of making the next refresh. And that's how this looks. Yeah, completely smooth, hitting 60 frames per second, and freeing up the CPU to other processes in between. The support for request animation frame is pretty good. It's been on desktop browsers for a while. It's kind of new to Internet Explorer and Safari. The story on mobile is pretty much the same. It's more recent on some browsers than others. But you can polyfill it really easily, and it is just dealing with vendor prefixes and then falling back to set timeout at the end. All you need to do here is use date.now as your timer, and everything's OK. As I said, jQuery does things the wrong way. It does things the lumpy way. But a small extension fixes that. And if you're doing animation with jQuery and you're not using this, you're kind of doing it wrong, because this tiny little bit of code will make your animation a whole lot smoother by using Requestframe. The reason jQuery just doesn't do this by default is because people have written code like this. So here we've got a carousel, and the carousel is moving every 5 seconds onto the next item. And then inside, we're starting an animation. SetInterval will run all the time, no matter what's happening in the browser, no matter if you're in another tab or another desktop. That SetInterval is going to run. Whereas Requestframe is smarter. It won't run if the user's in another tab or somewhere else. It will save the CPU because the user's not going to see the result. However, when you mix the two, we're calling next carousel item every 5 seconds while the user's in another tab. These animations are being requested but never actually happen. And then the user comes back into the tab, 20 animations try and start at once, and the page breaks. So don't write code like this. If you're wanting animations to happen every so many seconds, don't schedule the next one until the previous one is finished, because that means that the user can be in another tab, and it'll just wait. It'll just wait until the user returns in order to continue the animation or start the next one. The idea of syncing frames to refresh rates isn't particularly new. We were talking about films and TV before, and there was the same problem there. So in Korea, we were running at 60 hertz on TVs. Modern laptops also running at 60 hertz. But we want to watch modern TV shows and films on there, and they run at 24 frames per second. 24 doesn't divide into 60. So how do we display films on TVs? The solution was to do this. This is called Freebytopulldown. This means that the odd-numbered frames are on screen for 3 refreshes, and the even ones are on screen for 2 refreshes. The odd-numbered frames are on screen 50% longer than the even ones, and this is noticeable. This is really noticeable. Next time you watch a TV show or a film on your laptop, watch out for the smooth pans across the countryside. The motion is really, really juddery. You can see this effect of the frames being on the screen for a different length. And once you notice it, you cannot unnotice it. I might have spoiled watching films on your laptop for you. But hey, it gets worse. Your TV, if it's a reasonably modern TV, probably supports 24 hertz. It will go natively into that refresh rate. But the application that's feeding it video might not tell it to go into that mode, and you get the same problem again. I know Netflix on the PS3 is something, it drives me mad, because yeah, all the shows are displaying at the wrong refresh rate. We had a different problem in the UK, because we're on a 50 hertz screen. And once again, we want to show film at 24 frames per second. 24 doesn't divide into 50, but it nearly does. Ghostbusters 2 in the UK is 5 minutes shorter than it is here. Not because you have extra scenes, we just play the film quicker. We go from 24 frames per second to 25, and that divides into 50 nicely. Everyone speaks a little bit higher pitched, but you don't really notice it so much. So what we've talked about so far is all software rendering stuff. And I want to show the difference between software rendering and hardware rendering. So we're going to compare Internet Explorer 6 to what we see in Chrome today. So I've got a virtual machine booting up. That looks like it's working. So browsers discovered how they could do things on the GPU recently. And what that result... Oh, sorry, hang on. It did this to me before. OK, so we might skip this demo. Hang on. I'm kidding, of course. I'm just joking. But this is a really good example of the difference between hardware and software rendering. In Windows XP, the screen is a single canvas. The window manager knows about every pixel on the screen, but nothing more. The graphical representation is completely flat. So if you wanted to move a window, say this one, you would click and drag across. Windows will redraw it by taking these pixels and copying them to the new location. And then it identifies areas of the screen that are now displaying the wrong thing. So it would pick up these 3 rectangles. And what it will do is it will send a message down to the application now responsible for those and tells it to redraw this area. So in the case of this rectangle here, it says, hey, control panel, you need to redraw that bit, and it does. However, with the case of these other 2 rectangles, the message goes to Internet Explorer. But Internet Explorer has crashed, so it can't deal with the message. So those pixels stay on the screen. And that's why you can paint the window across the screen like that. That's how that effect happens. This is software rendering. A single canvas of pixels where the CPU adjusts it pixel by pixel. Things changed in modern operating systems like, well, Vista, but also OS X and many Linux desktop managers. The desktop isn't a single flat canvas, but rather a whole series of canvases, all stored together in the GPU. In this system, moving a window is really, really easy because the graphics card knows what every window looks like in its entirety. To move a window, the CPU just says to the GPU, hey, you know that thing you already know about? Put it over here. It's a very small instruction, and the GPU takes care of the rest of it. And once it knows all the positions, it composites them together into the picture you see on the screen. If you work in Photoshop, software rendering is like a flattened PSD. If you want to move something, you have to redraw what was underneath it. Whereas hardware rendering is like a layered PSD. Moving stuff around is really, really easy. The web used to be a flat canvas, but more and more is moving to the GPU, and it's about time because it turns out the graphics processing unit pretty good at processing graphics. We just haven't really been using it. Once the web browser knows where everything's going to go on the page, it then decides that particular elements deserve to be drawn separately from the rest. And once it does that, it'll draw them all separately and then join them together in an operation called compositing, and that will appear in the timeline. So here we have 2 paints and then a composite to bring them all together. You can tell which elements have GPU layers. Once again, Paul Irish showed this this morning. You would go into the cog there and turn on show composited layer borders, and you get this orange border on everything that's being accelerated. And this is updated in real time as well. You can see also these, this grid over the top. That's the tiles that are sent to the GPU. So each one of those is a GPU tile. So we can see here, there's, this is just part of the background layer. But when we click it to spin it around, we can see it gets a border as that transformation happens. So that shows things on the GPU changing. So what effect do these layers have? So here's a demo where I've got lots of these blobs sort of moving around in a circle. And the first thing we need to ask here is what the frames per second is going on, because it's not looking great. Here's what the timeline says. Every frame's taking over 100 milliseconds. It's pretty terrible. This is happening in the Windows XP way. We're seeing these full large paints like covering the whole canvas. Every time it changes, the whole thing is being cleared and redrawn. The animation itself is being driven by CSS. There's no JavaScript involved. We're animating top and left. Each blob animates with a delay to create that kind of snake effect. But what if we added translate Z, the magic hack? What if we added that to every segment of the snake, with the appropriate prefix, of course? Well, we go from this to this. It's a vast improvement with that one line. The timeline agrees as well. Those massive paints have been replaced with composites, and most of our efforts going into recalculate style and layout now. This is working more like Vista and OS X. All the CPU is saying is, hey, you know those blobs that I told you about earlier? Move them over here, and it all happens on the GPU. These slides are all just built in HTML, and they run smoothly because it's all just a series of fades and transitions, all the stuff that the GPU can do natively. So yeah, things like rotate, scale, skew, fade, that's all possible just purely on the GPU. So translate Z, we've seen this a couple of times today. It makes moving stuff around faster. Well, that's a little bean from the can of Jake's tips. But look closer. The best before date is today. And my partner and I have a little argument when this happens because as far as I can tell, she seems to think that food is fine, it is perfect, and then when midnight strikes on this date, it is now poison. And if you so much as touch it, your face will fall off and wasps will fly out of your neck or whatever. But no, it's just best before then. It's probably still okay. This is what performance tips are like. If you just blindly use them in a project, things might go wrong. So when people say something is faster than something else, give it a smell first because it might have gone off, as many rules have already. Don't trust performance rules. Use the dev tools to see what's going on. On the Chrome team, we say tools, not rules, which rhymes, so it must be true. But they're a great way to discover ways that you might be overworking the browser, or ways the browser might be overworking itself that you can hack around. But if you find the browser being slow when you don't think it should be, report bugs. I know it's annoying, and reporting a bug probably isn't going to help your current project because you need to ship tomorrow. But it might save your next project. So, translate Z. It got us to 30 frames per second, which is not great, but it's okay. But not only is it less than 60 frames per second, I've got this button in the middle. And when I click this button, it's going to run some JavaScript. And while that JavaScript is running, the animation stops. This is because the layouts and style recalculations that are going on here, they happen on the same thread as JavaScript. So when JavaScript happens, the animation can't run. We're currently animating top and left. If we switch this out for a transform, we get the same effect. We go from this to this. I don't know if you can tell from there, but the difference is astounding. We've gone from 30 frames per second down to 60. But not only are we down to 60, we're barely touching the system at all. It's taken 1.2 milliseconds to move 300 objects around. That's great. So to calculate style and layout, they were on the same thread as JavaScript, as we saw before. But composites don't happen on the same thread as JavaScript. So if we go back to the example, I'm going to click this button again. The JavaScript there is still slow. It's still going to take a while to run, but it doesn't disrupt the animation. The animation's happening on a different thread. That particular tip, that could change in the future, like all of these tips can. We might start moving more drawing stuff off the main thread, free more stuff up. But this stuff applies to mobile as well. So we can see from just animating top and left, and now we're using a CSS animation, difference is absolutely huge. Actually, animating these transforms gives us another advantage. When you animate, so on the left, I'm animating top and left. On the right, I'm animating using transform. And we can see with a transform, it can glide between the pixels, whereas top and left sort of snaps from pixel to pixel. Much smoother if you can use transforms. Unfortunately, this isn't true in Firefox. In Firefox, if you use Translate 3D, it's still going to snap from pixel to pixel, and they do this deliberately for reasons they haven't explained to me, but there is a ticket open for it. But you can hack around it. If you add a very, very small rotate, it fixes it. It means it can glide between the pixels, and it works beautifully. So if you're wanting smooth animations in Firefox, do that for whatever reason, and bug them about it, because it's stupid that we have to do that. So these layer things are great, right? They seem like this magic bullet. Let's take away some of these expensive styles. Let's get rid of the shadow. Let's get rid of the rounded corners, and let's make the colors alternate. So we're going to this. That's working fine. But if we take a look on mobile, we can see when these colors change, there's a huge pause in the animation, this huge bit of jank. And if we remove Translate Z, if we take that out of the mix, it turns to this. It's still not a great frame rate, but it's much more consistent than it is on the left, where it's stopping every time the colors change. What's going on here? Remote debugging can show us, and we can see this is where the pause is happening, this huge spike. And this is where the colors are changing. And we can see, each of those blobs, each of those squares in this example has to be repainted. And that's a lot of effort. On desktop, it's not too bad because it's got a good relationship with the GPU. It can get this stuff done really fast. But on mobile, redrawing all of these stuff separately and uploading it to the GPU is actually slower than just redrawing the whole thing. If we redraw the whole thing, as I say, we've not got a great frame rate, but it's consistent. It'll stay at the same frame rate throughout. So we've seen this translate Z trick to make layers on the GPU, but that's not everything. That's not everything that can create these layers. Here are some of the things that trigger layers in Safari and Chrome today. 3D transforms, which translate Z is one of them, but also translate 3D, rotate 3D, rotate X, rotate Y. Animating or transitioning using CSS, a transform property, an opacity property, or a filter property. For the duration of the animation, that will become a GPU layer. Flash and Silverlight, to sandbox them, that will be drawn completely independently and then composited afterwards. Canvas, for Canvas is hardware accelerated, that will be drawn on its own, as will video for the same reasons. Fixed position elements, something we're experimenting with at the moment is we're going to make them their own GPU layer on Retina devices. But at the moment, as you saw in Paul's demo earlier, you can put translate Z on these things and speed them up a lot. These can all change in the future. This stuff, we're going to be switching these things out, whatever's going to give the best performance on most of the sites today. Don't trust the rules. Use composited borders. Actually see what's going on your page, on your phone, and on your desktop. WebKit Nightly in the DevTools, they've got a really cool feature actually where it will list all of the layers and it will tell you why they're a layer. It's not always accurate, but it's quite a nice feature. This is something we'll be getting in Chrome as well. So these rules will change with time, but there's one that won't. Anything on top of a layer will become a layer as well. And that kind of makes sense because you can't layer something on top of a layer without it being a layer itself. But this can have quite a large impact on the page. So here I'm going to turn on composited layer borders. And this square at the top, I'm going to give this a 3D transform. So just of 1 pixel in the Y direction. And as I do that, you can see it gets this, there it goes. It gets the orange border to show that it's now a GPU layer. Now all of the rest of the text down the page is position relative. So that means that it's higher in the rendering stack than the box is, so the box will appear underneath it. And as I move that box down the page, we can see this text goes onto the GPU, and then once the intersect ends, goes off the GPU. So this is all using extra GPU memory because it's intersecting with, or it's appearing on top of something which is also on the GPU. And this can end up consuming more memory than you maybe intended, so it's great to look at the borders and see what's actually going onto the GPU. Because this actually affects rendering as well. And if you take a closer look, you can see the text here. You can see the color fringing. So on one edge it looks kind of orangey brown, and on the other edge it looks blue. This is subpixel anti-aliasing, and it makes text look really sharp on LCD screens. But as I move this box down, when the intersect happens, we drop down to grayscale anti-aliasing. Subpixel anti-aliasing can't be done as part of a composite operation, so we fall back to just black and white anti-aliasing. You might have seen this happen accidentally, like when an animation triggers, you see the text rendering change. This is why that's happening. If you've got a GPU layer and you want to retain the superior text rendering of subpixel anti-aliasing, if you give it a solid background color, you get the effect back, even if it's on the GPU. So by solid background, I mean no opacity. It could be an image, it could be a gradient, as long as there's no transparent pixels. And remember, things like border radius, they introduce transparent pixels as well. So if I add a border on here, there at the other side, we've dropped back down to grayscale anti-aliasing. Unfortunately, Chrome is more cautious when it comes to CSS animation. When an element is animating with CSS, it will take everything that could potentially appear on top of it right now, and it will promote it to a GPU layer. And this can have quite a bad effect on the amount of GPU memory you're using. You know, even if it doesn't intersect, we see these things down here are going onto the GPU as well. Because of this, if you've got an animating element, it's best to move it to the top of the rendering stack. And you can do this simply with something like z-index. And as soon as I do z-index 1, OK, it's appeared on top of the text, but all of the rest of the page has stopped getting a GPU layer per paragraph. And that can really improve the speed of things. Because we've seen the benefits of layers so far, and we've seen some places where they can they can be slower. But just having too many of these layers can cause a real problem. Not so much on desktop, but definitely on mobile. This is the Guardian website, and it runs at 60 frames per second. I was filming this with a 30 frames per second camera, so it doesn't look quite as fast as it is. But we can see from DevTools, it's running at 60 frames per second, and the GPU memory it's using is very little, 20 megabytes. So that's great. We want scrolling at 60 frames per second. But if in remote debug tools, I'm going to turn every element into its own layer. So just everything that's on the page. As soon as I hit 0, every element becomes a GPU layer. So I'm scrolling, and everything's fine. Everything's fine. I hit 0, and the scrolling just absolutely dies. And it's actually worse when you see this in real life than this recording. And we can see this here. We've gone down to like 25 frames per second from 60. And we can see why. It's hitting the top of the GPU limit. And then things are having to swap in and out. And that's where we're dropping all of these frames. Forcing something onto its own GPU layer is like drinking a cheap beer. There are some things that I'm better at after I drink beer, like, you know, talking to people and stuff. I find that quite difficult normally. A couple of beers, things are getting better. But when I have a few more beers, talking to people becomes a lot more difficult again. In fact, it becomes more difficult than it was before I had any beer at all. And that's what layering is like. Your desktop machines, especially the high-end MacBooks that I see so many of us have, they can really hold their drink. They can drink all through the night, and it's not a big deal. Your phone, I'm sorry, it's a lightweight. A couple of these, and it slurs all over the place. It can't do scrolling. It becomes awful. There are no magic rules around this layering stuff, none that will stand the test of time. They can make transforming and fading quicker, but just don't trust performance rules. Test what's going on in the browser, but always test what's going on the phone as well with the different hardware. So to summarize all of that, you need to care about rendering performance if you're not already, because if you don't, someone's going to come up with a product that does a similar thing, but they're going to care about rendering performance, and that's where the users will go. Care about performance by getting rid of this 300 millisecond delay. As a browser, we're working on it, and we're going to fix that soon. But existing browsers like iOS and older versions of Chrome use the Financial Times fast click because it'll just make it so much snappier. People have this impression that the mobile web is slow. I'm pretty convinced most of it is down to this 300 millisecond delay because it makes everything feel so sluggish. But it's stupidly, deliberately sluggish to wait for the double tap. If you're doing animation, use request animation frame. Give yourself the whole 16 milliseconds to prepare. And if you're using CSS animation, you get the same thing. It runs through the same timer. Use GPU layering to your advantage. If you've got something that's doing simple transforms or moves around a lot, give it translate Z or use CSS animations, and that will become a layer. But be aware of times when, if you're updating the contents of something frequently, having that as a GPU layer could be killing performance on your phone especially. And avoid too many GPU layers as well, either on purpose or accidentally by having your intersection or animations that run underneath other elements. Watch out for that. And with that, I think I'm out of time as well. So thank you very much. Cheers.